recording?
I'm not recording.
Okay, great. Cool. We can start. So this is where we stopped last time. And let's continue. There is one last item I wanted to quickly talk about, measuring of diagonal matrix elements. But before we get to that, there was another kind of an interesting and useful relation that we learned actually in this problem. So the circuit was drawn here, and we discussed that one way to construct this unitaries essentially is to take a linear combination of Pauli products, and if the Pauli products anti-commute, then you can normalize the coefficients, say CI bar, CI divided by the C2 norm, right? And then you get this unitary with this normalized coefficients. Okay, and okay, great. Now we could measure it like this, or turns out, which we learned from the work I will post. There's no probably reference here, but there is a work of Peter Love, again, the same person who wrote a nice paper on the mappings, Baravik-Kitaev mapping. So they found that actually there is a way to, if you have a unitaries like this, to present them simply as some other unitaries and only a single Pauli product out of this linear combination. Okay, so that essentially allows you to effectively simplify the circuit, right? And if you want to measure a wave function expectation value on this new unitary, sort of what we're getting is psi u psi, then this unitary could be presented like this, and one really can just put extra circuit and measure one Pauli, right? As simple as that. And then this unitary that we required is essentially some products of it turns out the products of Pauli products in this set with some i's in them, because they generally two products, they're Hermitian if they commute, anti-Hermitian. Okay, if they anti-commute, so see, then there, I guess i's are still will be necessary. Let's just check if pi. Oh, all of them are actually anti-commute, right? So if then they anti-commute, that simply means that pi pj, we check the hermiticity, then we're going to get pj pi, and this is minus pi pj because of anti-commutativity, and this is because of the hermiticity of terms, so we don't need really I here. So it's these guys are anti-Hermitian. The products of anti-commuting Paulis are anti-Hermitian because of this, right? And so we could always construct such unitaries that will take a single Pauli. Depending on which Pauli you take out of this anti-commuting set, you will get different angles. And it seems like this is kind of a particular case, but in reality, it turns out this is a general relation between Lie algebras and the algebras that are called Clifford algebras. Okay, so that's what I wanted to just quickly say as a kind of a generalization. So what Clifford algebras are? Clifford algebras, they are essentially can be built from anti-commuting sets. Like let's say we have Pauli's and they anti-commute. So then they could be a basis for the Clifford algebras. Clifford algebras as Lie algebras, they are first of all linear space, and the vectors in that linear space are Pauli products that anti-commute. Right, and then this is we have also identity, then Pauli products that are kind of anti-commute, and then we can build all products PIPJ, and then so on and so forth, P1 to Pn, where n is the number of terms here in the set. So we have generally 2 to the n terms in this set, and they all, this is dimension of Clifford algebra. Let's say Clifford dimension of Clifford algebra as a linear space is 2 to the n because it contains all these elements, and it's based on this anti-commuting relation. Generally, the Clifford algebras are defined not only for anti-commuting operators, but it's essentially initially could be thought as a generalization of the complex numbers, because in complex numbers you have identity and you have this special element I, right, complex unity, and one can think of complex numbers as also a linear space where every element is, let's say, A times identity plus B times I, right? And then there is a relation between this special unit, imaginary unit, and real unit, which is identity. And we know that from like elementary algebra, I squared is -1. And it turns out that this is general, something that could be generalized for the case where we have more elements, like the I special elements. So these anti-commuting Paulis, so they are special elements like I. Another example you may have seen in the more advanced algebra, so quaternions, IJK, and then identity. So those are the 4 elements in the quaternion algebra that is sometimes called H. And there are more complicated relation between IJK, but right now I want to just say for any Clifford algebra, what sort of is the idea behind this special units. And the idea is the following. So if we have, I guess in general, I didn't introduce general notation, but let's say if we call this is a special unit, and this one will be some EI units, and this one will be EIJ units, and then this one is of course up to let's say some sort of J, but multi-index quantity, right? So these are basis vectors. And so the idea, what essentially defines the Clifford algebra, is the fact that we have a relation between these basis vectors, A and then B of some sort, equals to eta AB and then units, right? So this is anti-commutator, and this is diagonal matrix, and at the AB is a diagonal matrix which contains, let's say, P once on the diagonal, and then Q minus ones, and generally are zeros. Right, so others, it's diagonal matrix, but essentially it has P values of ones, and then Q values of minus one, and R values of zeros. So this is the most general definition, and the idea is that P plus Q plus R equals to the n, the number of these yes, elements, basis elements that we have here, right? And so now we could see how any Clifford algebra with this definition is applicable to complex numbers and to the one that we introduced based on the anti-commutation between the Paulis, right? So the idea here is that for complex numbers, I guess probably the well-known example for us, we have only single basis vector, right? And so there is no anti-commutation with anything else, right? So it's just I with itself, and then I with itself, it's exactly this relation. So anti-commutator of I with itself, I gives essentially 2I squared, which is minus 2, right? So this eta corresponds to just a single Q, which is minus 1. And generally, Clifford algebras are the notation is PQ R. So in this case, that would be C0, 1, 0, right? So this is notation for the complex numbers. And for our Pauli products, there will be just more anti-commuting terms, right? So they we know that for every Pauli here they anti-commute at us as it's supposed to be essentially well, it's diagonal, right? So AB, if A and B are different, then eta is 0. But if A and B are the same, then eta is equal to 1, right? Because so we have a relation for any Pauli product is that pi squared is 1. Okay, so this is kind of a general introduction into Clifford algebras, and they are useful because appearing from kind of any set of anti-commuting Paulis, and we'll see them as well in terms of actually fermionic variables. You can also introduce Clifford algebras, but right now I want to kind of get back to this problem.
Can I ask one
Yeah,
question?
sure.
So how does it relate to Clifford gates, where we also have the Hadamard?
Yeah, great question. I believe in the mathematical literature, Clifford group, unfortunately, is not very commonly used. I think they have a different name for that. But the idea is, as I understand, and that's my interpretation again, I haven't seen any rigorous mathematical text where they would be explaining the Clifford group, Clifford algebra relation. My understanding is Clifford group is a group that acts as, I believe it's called normalizers, meaning that the group element acting on, let's say, a Clifford algebra generator, Pi, translate this into another Clifford algebra generator. So you will always, with a group, you will get basis vector to a basis vector sort of relation. Right. So that's kind of my understanding of the relation between Clifford group and Clifford algebra. And both are exponentially large. So both are somewhat inconvenient, but Clifford algebras, they are, well, the nice thing about them is that they're linear spaces, so we can do many things that we can do in linear spaces, find the solution of linear system of equations, things like that. But what else is very nice, that's what I'm trying to get to, is it turns out whenever you have a Clifford algebra, you can organize small Clifford group, Lie group and Lie algebras. So that's nice because in general, there are nice relations that one can establish using the Lie groups and Lie algebras. One relation we already talked that if you wanna say diagonalize some operator, bring it to a simple form, then if that operator is linear combination of elements from the Lie algebra, then rotations with a Lie group element corresponding to that Lie algebra makes the form simpler. So this is what's happening here, because all these elements, PIs, they anti-commute, and I will show that they actually form the Lie algebra. And therefore, these elements that are Lie group elements, they can diagonalize or sort of simplify this kind of linear combination into very simple form. Okay, so bringing it to a single element, and why I'm kind of referring to this as kind of a diagonal form, because we know in general in Lie groups, so Lie algebras, diagonal elements correspond to fully or like largest mutually commuting subset. And because all these guys are anti-commuting, the largest set of commuting elements is just a single element. Okay, that's why this is kind of equivalent to diagonal. Or we can also say that any linear combination of Paulis that anti-commute, they are equivalent to a single Pauli or a single qubit operator, right? Because there is always, using again Clifford group, we can always transform any Pauli into just a Z1. That's kind of nice property, which we discuss as well. It's related to the way we measure commuting Paulis. But first, let's just establish very quickly that if we have the anti-commuting set of generators for Clifford algebras, we always have Lie algebras based on that set. And that Lie algebra is very easy to generate. And the only thing it contains is on top of the anti-commuting elements are quadratic elements, these ones. And we could easily show that there is nothing else there, meaning that if we have anti-commuting Paulis, right? So Pi, Pj, they don't commute. We already saw that this will result in Pi, Pj with coefficient 2, right? So this is not initially a good sign, right? So you start commuting things and you're getting something that is not from the set. You might be disappointed, thinking that, okay, it's gonna keep growing, but anti-commutativity actually stopped this from growing, because you could see that, okay, let's say Pi, Pj now will commuting it with P, let's say K, right? What are the possibilities? So this is just Pi, Pj, Pk minus the Pk, Pi, Pj. And if we move K from left to the right, it will essentially change the sign twice, right? And then we'll, if K, let's assume the K is not equal I or J, right? They're not equal, then when every time we change the position, exchange them, we get -1. So 2 exchanges gives us +1. And so this term and this term will be exactly the same. So we will get in this case 0 commutator, which is nice, no new terms. But now if we consider the case where k equals to I or j, presumably I and j are different, so it cannot be equal to both. So in that case, simply what we get is this case. Let's say if pk equals to pj, then we got the square of Pauli, right? And that's going to generate pi only minus, and in this case, pk, in order to recombine with pj, which is it's equal to, we need to change through the pi, and then that requires changing of the sign. So there will be again pi multiplied by 1, which comes from pk reunited with pj. And so what we got in this case is 2 pi, right? So in that case, it's either 0 or the element that we already had in this in this set, right? So we didn't get anything new. And now the only last thing to actually to consider is commutator of pi pj with, say, pk pl, and there are a few cases. One is that k and l and I and j are absolutely different, right? So then in that case, ij is not equal to k or l. In that case, simply we move both of them through I and j, and that's 2 exchanges. 2 exchanges doesn't change the sign, so we get the minus of the same sign of the same term. So that gives us 0. And then in the situations where one of them overlaps, either j and k overlap, or k and I, say, overlap. In that case, well, whatever is overlapping, that is getting destroyed because the e square is actually 1, right? And so out of the 4, we're gonna get something like pi p, or let's say l, if j and k are the same, with factor 2 usually. So they're getting destroyed with plus and or minus, depending on which ones overlap. Okay, and so we're again getting back something that we already have in the set. And if all of them are the same, then you're going to get simply 0, because well, if they are identical, then the commutator, of course, is 0, right? So in both cases, when there is no overlap or there is a total overlap, there's zeros. And in the case of only one index overlapping, you're going to get the quadratic elements. So what we've shown essentially that you can close the algebra if you take anti-commuting Paulis and all the products, right? And that is nice because it's just whenever if you have n anti-commuting, then you can always diagonalize linear combination of anti-commuting and their products. Always, this is easy. That's why we can always measure any linear combination of anti-commuting Paulis. Okay, so because there is a unitary that brings it to a single Pauli, and then if it's a single Pauli, then there is always Clifford that brings it to the Z1 that we can measure. Okay, so this is the story of kind of relation between Clifford algebras and Lie algebras. It works this way. Unfortunately, it doesn't work the other way. So meaning that if you have the algebra, that doesn't mean necessarily that you can find anti-commuting and their products that would correspond to that Lie algebra, right? So that's the relation. All right, and then what this scheme also allows you to do in general is to measure not just expectation values, but rather elements with the different wave functions. So it's matrix elements essentially. Okay, before we get there, are there any questions regarding these things that I just described?
More general, so how do we actually do is that then just an arbitrary mapping we choose to do to get H into a sum of unitaries?
Okay, we always have H as a linear combination of Paulis.
Yeah.
Right, so those are unitaries.
Yeah.
You can also group Paulis into anti-commuting. That's the.
But use the same like use for the measurement, for implementing it on a circuit. Like Jordan-Wheaton or whatever.
Okay,
you can do the same thing as for measurements.
Well, you do these decompositions classically, and then you try to implement unitaries that you decided to kind of use. Like, let's say, simplest case is a Paulis, then you could just do the controlled Pauli rotations, right? So does that answer your question? Or okay, good. All right. So anything else? Yeah.
This is orthogonal.
Is it orthogonal? Yes, if you introduce for orthogonality, you need to introduce inner product, and usually there is a way to introduce, like let's say with Paulis, there is a like in the operator space, one of the inner products which could be used is trace of AB divided by dimension of the space of C, I guess in this case, right? So that can be used then to show that the basis is orthogonal. So since we have only a single board, I will arrange this. Okay, so I know we talked about VQE in general, but there is also possibilities to simply maybe construct some states on the quantum computer and build the matrix element of the Hamiltonian using these states. And then matrix elements of the Hamiltonian would be needed. But the whole point of doing that is, let's say, your states could be some unitary ansatz applied to a simple state, Hartree-Fock, and then the idea is that in VQE optimization is so expensive, measurement is expensive, so you want to minimize optimization of the function, right? And so one can suggest to let's construct the total wave function as some linear combination of basis functions by i's, but we want to use quantum computer somewhere, and so the idea is to introduce this quantum complexity, quantum entanglement that the unitaries will bring. But instead of optimizing these unitaries, we can simply use the power of linear algebra, construct the matrix of the Hamiltonian, right? So this is the matrix in some basis, and then solve what then will need to be a generalized eigenvalue problem, right? Generalized because these unitaries, they are not necessarily orthogonal. So if you have a based on a Hartree-Fock state, then or any other simple state, you will get potentially these matrix elements with different hues. Okay, and so these are so-called subspace expansion methods that people tried. Recently, IBM, I think, had the paper, because IBM is kind of very adamant at getting some, I guess, quantum advantage in near term, right, quickly. So then, to avoid optimization, which is slow and expensive on the quantum hardware, they were exploring possibilities for building the functions using some unitaries that are easily implementable, and then one can diagonalize, say, things like this. And I believe they called it Krylov subspace methods, Krylov methods, tested on the not chemical problems, but the problems with some condensed matter Hamiltonians, either Heisenberg or Hubbard. Okay, but at any rate, one can ask the question, how do we calculate these matrix elements? Because this one is just I guess, a simple version of this, where the states are different. And well, actually, it's not surprising that one can just rewrite this in terms of just the same state, and then UI dagger. If you have LCU linear combination of unitaries expansion for this, or let's say H is presented already as a linear combination of to make them different, I will put V here, right? So V and UJ HF. Right, so then this the nice thing about unitaries is product is again unitary, so one can simply use this circuit to implement things like this. Okay, very straightforward, but turns out that you could actually do even sometimes better, meaning that you don't need to really do this in order to use this circuit. The fact that we have Brian get different, actually, we could sort of make a normal scheme. Normal meaning that we could create a wave function in a larger space that acts that we calculate expectation value of the Hamiltonian in a larger space. So something like this needs to be measured, and that will provide information in order to get the phi I, H, phi J. And the nice thing about this, we sort of, like mathematicians, return back to the problem that we already know how to solve. Okay, so the only question is, two questions: how to construct this essentially Hamiltonian in extended space, and how do we construct the function in that extended space. Both actually solved quite easily. We can just add one single qubit so that we can construct psi L written as 0 on this ancilla qubit, phi I, plus 1 of that ancilla qubit, phi J, and with the normalization square root of 2. Okay, and then the Hamiltonian in extended space is the real Hamiltonian, the Hamiltonian that have in the normal space, tensor product with sigma x plus I sigma y for the ancilla. You could add the 1/2 to make it more canonical, because what this is, with 1/2, it's just the sigma plus. So it's a raising operator. And essentially what we created is the operator that is, well, this is Hermitian, right? and this one is not. So if we have a product of Hermitian with the operator that is not, and they are commuted because they're acting on the different qubits, this one is ancilla, and this one is a target. So then essentially we're getting an operator that is not Hermitian. But that's okay because we could write it as a sum of two Hermitians. One Hermitian is going to be L, let's say, like L1, then and plus, you could say H L2, right? And then HL1 is H tensor product with sigma x, and HL2 just H with sigma y, right? So we measure these two because they're measurable. The same methods as like we used for the measure in H, because this the same partitioning could be used for H. Then you just add the extra qubits and yeah, then combine the results. But and don't forget that, right? So one thing I didn't yet, I guess, explain is why this works, right? So why can we get from this state with this Hamiltonian the necessary matrix element? But that is relatively straightforward if you consider that, well, let's say we have a state like this, and then on a state like this, if we act with a sigma plus, what this sigma plus will do for the zero ancilla, it will essentially create the ancilla in the state one. But in the case of one ancilla, there is nowhere else to raise, right? So it's already the highest weight vector in that two-dimensional space. So you're gonna get just the hue of that state. And so when the sigma plus is acting on this superposition, then it just leaves this part, right? And the bra part is the whole thing, but when we do essentially calculations, the part that if you don't have a one, well, it's not okay. So we could just put out, right? So it's a 0 with phi I plus 1 with phi j, right? This is going to be bra part, and then it will be H sigma plus acting on the 0 phi I plus 1 phi j. We'll use them as like coefficients, right? And so what sigma plus will do, it will destroy this guy and will turn this guy into essentially H acting on phi I, and then 0 will turn into 1, okay? And then on this part, the only thing that can couple to 1, because there is no more, essentially we already used up that ancilla qubit, is the 1 phi j, because the 0, 1 will be orthogonal. So this is what you're gonna get. And 1 times 1, because there is nothing else acting on ancilla. So this is gonna be phi j H phi I. So this is the matrix element we want. Okay, so as you can see, even though we can do with this circuit of diagonal elements, we can also do them using extra qubit in this way. So, and according to our my group studies, essentially, which haven't been published yet, but it turns out that this way with where we can use the grouping again works better than the way that requires doing the linear combination of unitaries, simply because this is more sort of a restrictive way of doing things. Yeah.
So if you do this, you only really use the quantum circuit to construct the matrix elements, right? Because the diagonalization still has to be done classically.
Yeah, that's right. Right, and that's a way to avoid maybe optimizing unitaries too much, because in VQE, what people need to do is to optimize unitary so that it gives the lowest energy. But if you have small matrix, presumably these unitaries are already somehow capture good amount of quantum effects. Then if you could construct a small matrix problem, then classical computer can do it. Yeah. So, any other questions? All right. So, just to finish, I guess this is all for this part, and we could just move on to the next measurement scheme. And this measurement scheme is effectively what the idea here that one could explore is with, like usually if we measure things in a normal circuit, we apply some unitaries and then we do measurement of qubit 1, qubit 2, qubit 3, and so on. But one can try to sort of after measuring the first qubit and getting the result, see if this information can be used to improve the measurement of the subsequent qubits, right? And so, because information is valuable, or you could try to make it valuable and figure out, okay, how do I use the knowledge that the collapse of the first qubit gave me a 1 instead of -1, then can it be somehow leveraged to reduce the cost of subsequent measurements? And how can we use the information? We decide based on that information here to put extra unitary. What sort of unitary do you want to put, right? So that's the idea of this circuit, right? So that we have construction of the wave function with this of 2 qubits with the general unitary, and then we measure the first one, and based on the result of the first one, +1 or -1, we decide whether to maybe use the V extra unitary on the second before the measurement, or well, one can think of like using different V's depending on the result of the first measurement, +or -1, right? So that V1 and V2, and that's the decision making one can do. And there are like hardware ways of accomplishing this, right? So okay, so what does this really allow you to do? If we look at the simple example there, in the kind of having identity on the first qubit multiplied by x2 plus z1 and then y2. Let's say the Hamiltonian is written like this, and we could see how the circuit will work in this case, to like how the measurement of the first qubit could be used to our advantage. So the idea is that when you measure the first qubit, you essentially substitute operator z1 by the number, right? So you learn that z1 is +1 or -1, and that the first collapse, you then need to deal with either, let's say, small h +1, that is x2 plus y2, right? And that's a single qubit operator. you could always find rotation within the SU2 group that will bring this to essentially Z2, right? And this will require some rotation that is based on essentially the fact that we have plus between X and Y, right? And if we have H minus 1, then the rotation will be different, but still doable. The rotation will be from Z2. Rotation will be still from SU2, but the angles will be different because they need to bring X2 minus Y2 to the Z, right? So that's the kind of the basic idea. And one can do sort of many cases like this. In some of these works, we discuss how in the normal Hamiltonian, one can try to find the parts that satisfy the condition that you could sort of peel the part as like an onion, right? So you sort of always have a situation where you could first maybe measure first qubit, adjust the rotation for the second qubit, and then so on and so forth, right? But later we realized that all that can be also formulated using the multi-qubit unitaries, because what is going on here is simply you could formulate as a single 2-qubit unitary that takes as a generator, let's say generator for the second qubit rotation, if it's plus, based on the projector of what's happening with the first qubit. So it's a projector on the plus state, so Z1 is plus. And also we could have a generator for the second qubit for the minus case, if there is a kind of 1 minus projector, essentially, right? So we could always build unitary that is based on a 2 qubits transformation instead of doing one after another, right? So that's a flexibility. Some machines like Honeywell, I believe they allow this midstream measurement, and that reduces essentially reduces the necessity of building the 2 qubit unitaries, and if you could do adjustment based on essentially the 1 qubit measurement, and then adjust what's the rotation for the next qubit is, right? So to show this is indeed the case, let's just see if we have a exponent of simply speaking, this exponent is always going to be exponent of two elements separately, because projectors, they commute, and then you could see that each of them is unitary because okay, so what we have here is exponential of this type of terms will be Taylor series. Let's say if we have 1 plus G2 plus G1 plus so on square, so on. But then it's plus 1 plus, then projector can be removed from this consideration, because projector in any power is still projector. And this will be then P1 plus minus and this will be the exponential part, G1 plus and multiply by projector. So this is just I introduce a 0 here. This gives me everything. This is 1, and I want to. This term is what it was here, but it has an extra P1 plus. So yes, I need to put P1 plus here. Here's 0. So this is the form, I believe, because projector is kind of removed from the exponent. And I want to remove it from the first term. That should be 1. Okay. All right. So then the final expression is 1 plus this and minus P 1 plus. So this is the expression, or you can write it in terms of this being essentially P minus 1, right? Because projector onto the plus state and minus state, they're complementary. So we have resolution of identity 1 minus plus P 1 plus, right? Therefore, this is what this function is going to be. And similarly, we could write also we have P1 minus P1 plus commutator equals to 0. That is simply because P1 plus and P multiplied by P1 minus is 0. They are orthogonal, and P1 plus we can define explicitly as well, let's say 0, 0, and P1 minus is as 1, 1, right? And then what is gonna be is one of these products is actually P1 minus plus exponent of generator P1 plus. As you can see, what we're getting is well, here technically we don't do anything on the second qubit identity, and then this guy that is the opposite. We just switch plus to minus, right? So it's just like this. G here it's G2 plus, and here it's G2 minus, P1 minus, right? And so what this is really a controlled unitaries. If you remember what we discussed last time, like yesterday, control not was written as essentially projector to 1 plus times identity, and then projector to 1 minus, and x 2, right? That was C naught, where we check the first qubit. If it's a +1, we don't do anything. If it's a second qubit, so if it's a -1, then we do the flip of the second qubit, right? So similar story here. Effectively, this type of unitaries, they can be split into two terms. One is controlled based on the we do something if the first qubit is collapsed to +1, and you do something, you don't do anything if you do the opposite collapse happens. And here this is the opposite situation. You do something when the collapse is to -1. So all these schemes technically can be we could do midstream measurement, or we could just substitute midstream measurement by this more complicated unitaries, which will do the work. Okay. All right, but with all that, I guess we have a recent publication 2305, the first archive reference there, where we discuss how the fragments could be found, and in fermionic space and qubit space. Turns out these projectors could be constructed in both situations, but search for fragments and optimization of the variances in these cases is relatively complicated. So yeah, that complications are one needs to be aware of. So let's probably make a break, and after the break, we'll get to the next topic, POVMs. Okay. Yeah.
So what is the actual application for this measurement scheme? Because so would you use it to calculate overlaps?
Oh no, this scheme is just figuring out a different fragment that one can address.
I mean, these control U operations you would have in Hadamard test. So you could simplify your Hadamard
test. Right, but here the control U is sort of working differently. It's a different type of fragments that we can address using these midstream measurements or controlled rotations. So essentially,
okay, so you would do that in a VQE scheme. Okay, so that's now not in Hamiltonian on the device. Okay,
right? Yeah. Sorry, I didn't mention that. Right.
Oh, yeah. Okay. Yeah. We now back to VQE.
General. Yeah. Right.
Can you still do post-selection when you do that?
You do post-selection. You do selection of unitary based on what you obtain. Essentially, what you're doing is you're projecting one qubit, and based on what that one qubit is sort of telling you, you act on the whatever is left differently. So post-selection, it is sort of a version of a post-selection, but post-selection usually is mentioned.
You can still do post-selection on the remaining part. I mean, so like on the V part here.
Yeah, but the post-selection usually comes in the discussion of the error mitigation, right? Yes. So here we're assuming ideal case scenario, and indeed, well, you cannot probably avoid in general having +1 or -1 in the result of the measurement, and you don't use this to see whether there was an error or not. You just use it to.
Yeah, but in general, you could still do, like if let's say we are in a Jordan-Wigner mapping and we want to conserve particle numbers, but we're a noisy device, we can still then do such a post-selection looking at our bit strings are still
Right, but
Conferring the particle numbers if we are in a noise device as kind of a mitigation scheme.
mitigation. So for mitigation,
Oh,
yeah, we need to know what is the right and what is wrong, right? So what is the right value, +1 or -1? Here we just essentially allowing ourselves to deal with the more complex fragments where both values could be possible, right? So don't forget this simple example I gave really here is that based on what result of the Z1 measurement was, you adjust the next measurement for the second qubit, right?
Yeah.
And you could only do that if you know what Z1 is. Otherwise, you don't know in what frame to measure.
Yeah.
Right. So if you don't do that, the only sort of fragment you could do the measurement for is essentially not a sum, but some sort of you would need to have either x2z1 or y2z1, or you cannot have a sum like this essentially, right? So that's just increasing the sort of way we can what sort of fragments we can measure. Okay. Maybe another example one can see is that for the fermionic Hamiltonians we talked, right? So anything that is single electron, like excitations with some coefficients, right? So anything like this, plus conjugated version. Anything like this could be measured, right? Because we can diagonalize. Now imagine we have some occupation number that is not in this range, and it is projector. So I is not in the P or Q, and then we have let's say this projector and something like PQ DPQ here, plus Hermite conjugate another fragment, but here we have a complementary projector. So anything like this now can be measured, and formally this is now 2 electron fragment because this is 1 electron and this is 1 electron. So technically this is 2 electron, and we could measure the entire thing as long as we measure this qubit first. Then we know how to rotate this part, but if we collapse here, we know how to rotate this part, right? So that's kind of the idea that now we can address bigger fragments. Unfortunately, from practical simulations, we found that this type of fragments are less potent than the fragments that we already involved, where we don't need to do this kind of choosing effectively what we're doing. We're finding Hamiltonians, which are 2 electron Hamiltonians. Eigenstates of these Hamiltonians is still Slater determinants, but depending on occupation of a certain orbitals, the other orbitals should be rotated differently. So this is type of the Hamiltonians we can address, but they are not that interesting in the sense that the real Hamiltonians are not like that. Okay, so you don't benefit much by considering those.
But does it ultimately lead to a reduction in measurement?
It does not compared to the other techniques. So in some cases with the qubits, in this work 2305, right? So we've shown the examples where in qubit case there is a benefits of this finding such fragments, but for the fermionic case we didn't find in fermionic algebra we didn't find the cases where it's benefiting the measurement scheme.
Okay, so and neither the variance, or is it then just
it was with variance last work. So first we discovered this scheme in this paper by 2019. It's published already, but then there we were worried mostly about the number of fragments. And then we start looking at the number of measurements, and in this most recent publications, we found that indeed there are actually complicated graph schemes that allow you to find such fragments, and such fragments, when found, could be made with smaller variances essentially. So it's helpful, but yeah, going into all the details, it's a little bit complicated. All right, let's continue. And this is the work that some of you may have seen. It is the work that uses a different kind of measurements called POVM measurements, and POVM, what it stands for, it's a positive operator value measurement. And what we've been talking so far was the normal projective measurements, and POVM is generalization of that. Here, it turns out this generalization could be useful, although the Hadamard test could be also seen as a particular sort of version of that POVM type of measurements, because in general, we'll see that this new type of measurement is the best way to think about it is the projective measurement on just a bigger system, right? So, but everything, let's just unpack a little bit. So the normal projective value measurement, we have, let's say if we have a state, it's in a superposition, 0 or 1. So then we do the measurement with the measurement operator that is either a projector to the 0 state or 1 state, right? And so these measurement operators, what they do, they sum to 1, and they are orthogonal projectors, meaning that mi squared is mi, and mij is delta ij mi, right? So this is the normal projective measurement. Now what POVM is generalization of that with this condition satisfied, right? So we have to call them differently. Let's say it's Fi, and this is a notation from Wikipedia, right? Fi's, they are projectors, but they're not orthogonal. Okay, so one can think of them as just a set of operators. They are positively definite, so they could be some states. We'll see. But that's pretty much all. And so to get some idea of, and they're positive definite, so that means that Fi, let's say they could be written as a Ki dagger, Ki, some operators. And they're Hermitian, positively definite, and simply means that any vector phi with the Fi is always more equal than 0, right? Because if you put this sort of definition of a phi, then it's then this will become simply phi Ki dagger Ki phi, and this is like norm of the Ki phi vector. So always positive. All right, great. Now, how do we really get something like this? And why do we need such generalization? Well, this is the paper where this generalization was used, and you will see in a moment what's the benefit. of this generalization. But originally, if you look at the, and I'll put it in reading sources, if you look at the problem of distinguishing states, if someone gives you states and you want to do minimal number of measurements to say what state you're given, so POVM measurements, they have some advantage with respect to the projective measurement. But I don't want to go into the details of that example because there are some subtleties like what exactly is meant. So like how, like essentially, it turns out that if you are given the states which are non-orthogonal, meaning that there could be state 1 and state 2 that is given to you, and the overlap is non-zero, then there is no really way to do like one measurement and figure out which state is given, right? But in the situations where you use POVM measurements, you could do this better than in the case of PVM. So this is the kind of the story, but it's not related very directly to what we are doing. Here, what we are trying to do is to study the expectation value of the operator. And one question we could ask is, okay, so what is this, like how do we realize this POVM measurements? And this is what was done in this paper, and in general, one can reduce the POVM measurement to the normal PVM measurement, but in a bigger space. All right, so what I mean by that, imagine if you have a situation where, again, we start with some maybe superposition state like this, and then we introduce, this is pi state, and we introduce ancilla, and then do the unitary transformation that couples both. And eventually, let's say if we just measure the ancilla, then one can see this as a sort of interesting way of kind of modifying the state that you obtain here. Now, what's going to happen is this unitary, let's say if it's completely general 4x4 matrix, right? Which could be anything. Now, if we start with this state that is alpha beta 0, 0, right? Then we apply the unitary and we get C1, C2, C3, C4, right? In the basis of, let's say, 0, 0, 0, 1, 1, 0, 1, 1. And then when the measurement happens on ancilla, there are two possibilities. We collapse to 0 or 1 state. And what this leads to is essentially what's going to happen with the target state. We could just write down, because if the ancilla will collapse to 0, then what this means, here I didn't define what's the target. Well, let's say this was a target and this was ancilla, right? So if ancilla is 0, so those are the two states that our target system will be in. And this means it's a C1, 0 plus C3, 1. This is the resulting state. With some renormalization, of course, because we had this state for the larger space, right? So that means the CI absolute squares, they were equal to 1. So here C1 and C3 only present. So this sum of the squares is not 1. So we need to renormalize this by C1 square plus C3 square. And this is the state, let's say chi 0 for the target here. What we obtain if the collapse will happen on ancilla to 0. And if ancilla collapses to 1, then we will get the result that is correspondingly C2 for the 0 plus C4 for 1, right? Divided by the C2 squared plus C4 squared. And so this is say chi1. So these are the states that we will obtain, and the probabilities of these states. Where do we get those? Well, they are simply if we know the state here, then the probability will be corresponding to C, let's say 1 squared plus C3 squared. That's for the chi0. That's the probability. And for chi1, those are correspondingly C2 squared plus C4 squared. That's probability for chi1 state. So we could generate the states that by collapsing ancilla, and this is what's happening with the target state. Generally, probabilities here are given in this formalism by simply this, I guess. Yeah, we have phi's. Yeah, probabilities of getting result here is phi. It's phi operators, and so they sum to 1 because phi's sum to 1, and this is how the POVM can be seen as a sort of result of the measurement in a bigger space. Okay.
Sorry, I don't. What's the connection from the center to the right?
Center to
What
the
is
right.
what is the F in your example?
In this example, right. So what would be the F in this example? Let's see. So the F in this example will be the operators that let's see, if F is some projectors,
like, are they in the U or what?
yeah, so the U, of course, will define what the kind of the result is, right? So then technically, yeah, let's see if we have yes, so that can be derived by the following statement. So if we look at the probability 0 or 1 that we got there, they are related to phi's, but on the other hand, they are also related to U because the operator for, well, let's say for 0, right? So we did the collapse eventually here for the 0 state for the ancilla. So that's a 0 operator, but then it's a 0 times identity on the target state. So this is the operator, and it was applied, there was a unitary applied, right? And then that was applied to phi zero state by zero state. Okay. So therefore, if we wanna define something of this kind, Fi applied to, let's say, F0 phi, right? So then F0 will be 0 unitary, then this, right? But one needs to understand that this lives in the bigger space, right? So it's on Silva target, it's a okay 2-qubit space, right? And so that clearly it's the operator where this is a single qubit, let's say K0 dagger. This one is K0, right? So you have two operators, each single qubit, but yeah. So then you would, after defining the U, then you would see what the operator is. Okay, so we could define a particular U, and okay, so that might be one way to address this. So let's say if we, well, so what's the general form for the 2-qubit U is a linear combination of potentially we can have either linear combination or product. All right, so something, what can we do? We could do pretty much anything we want, as long as it's unitary. So parameterization for the unitary would be product of Paulis, that 2-qubit Paulis. And yeah, so we could make single Pauli to make it simpler. I guess the result that we want to see something, I guess non-orthogonal, right? Something like that. Because after all, this is already a single qubit operator, right? And there is not much to say more. And then there is an analog that is F1 corresponding to having one here, right? And well, okay, let me continue with the actually the POVM that they use, and then I think it will be a little bit clearer what exactly the F0, F1 that we end up having. Well, they call them pies, right? But yeah, this is a little bit, I understand, a little bit abstract, but I guess the main point here is that this still is a resolution of identity, all these POVMs, but they are non-orthogonal. And one way to think about them is that something happens in the bigger space, and that corresponds to projection into some space, some states which are non-orthogonal in the target space. Okay. Now, but for us, what will be important is this notion of information completeness. that was used in this work. So the idea is that let's say if we use PVM again, 0 projection or 1, those are the projectors, right? Then if someone gives us the density, then and we could only use these guys, so that we won't be able to well, kind of represent the entire state that is given, because generally the state that is given on the block sphere, well, it's a vector, right? And that vector state phi, right? That vector could be fully characterized by knowing what the 3 Pauli matrices expectation values are, right? Because then, if you know that, you could simply write that any single qubit operator expectation value is simply the sum of sigma q's, some coefficients here that's coming from the 1q, q, sigma q. Okay, so we can always find the expectation value if we know these guys. But then if we do the measurement just here with the PVMs, then let's say we know the expectation value of sigma z, right? Because sigma z is simply 0, 0 minus 1, 1. So we know that exactly, but we don't know anything about the sigma x, sigma y part. Okay, so that's what we're missing. So whatever the projections here could be, that information is not available to us, and therefore that's kind of the one can see as a motivation for going to POVMs. It turns out that in case of POVMs, there is always like these FIs that are in the case of a single qubit, there are 4 FIs that form the identity, and the way 4 comes like y4, this 4 is 2 squared, right? And usually if the dimension of the space is d, which is for 2 qubit space, for qubit for 1 qubit, it's d equals 2, right? Then you need a quadratic number of POVM operators that will allow you, essentially, if you measure these POVM operators, phi's, for the state that you're given, phi state, you can measure all these phi i's. Then from these phi i's, what you can do, you could recover the values of sigma q.
So we try to find an approximate way to do quantum state tomography.
That's right. Yes. So that's the bottom line, is that if we look at the problem, of expectation value for the Hamiltonian as a state tomography, meaning that we are interested in what state did we prepare, even though we sort of in between, we prepared the state, and now the job is to figure out what this state is. In order to, if you know the state, presumably you could obtain the expectation value of the Hamiltonian, right? And so, but The problem is that we don't know state very well, and therefore we're measuring it. And if we think about a single qubit case, that's easiest to think about. The question is, what operators can we measure so that on a quantum computer, so that you get back the expectation values of all the Pauli operators, and that will give you the knowledge of any operator essentially, because you know the coefficients, and then you can do the sort of you can do this reconstruction. Okay. Now, okay, so this is the kind of the basic idea of POVMs that are so-called informationally complete. There is also word symmetric, symmetric informational complete POVMs. It's the POVMs that if you measure all of them, then it will allow you to reconstruct the state. Okay, so that's the idea. And in the one qubit case, this okay, written here, there are 4 states. We can write these FIs explicitly, and of course this is not a unique choice. You do the interpretations, obtain something out. But this one example of states, like let's say for the 4 states, so essentially FIs become like we will define the projectors by 2. That's for some notational reasons, and then projectors will be built out of these states, psi I, and these are the 4 psis that allow you to learn essentially about the one qubit case. So it's 0, then 1 over 1 over square root of 3. Remember 2 more with everywhere we have 1 over square root of 3. Plus different phases on this term. Shown on that picture here. That's the picture of these states. So then with these states we can organize projectors. Okay, so the projectors are not orthogonal but they sort of have an interesting symmetric property that projector like this give you generally dimension, which is 2 for the one qubit case, ij plus 1 divided by d plus 1. Okay, so this essentially some conditions that allow you to essentially recover the one qubit state out of this after measuring the state with these 4 projectors. You could recover all the actually Pauli matrices. Okay, and this is essentially what is done in this work. Now, my example where we had a single qubit and then 1 ancilla. was an example how to essentially create this non-orthogonal projections by introducing ancilla that allows you to essentially couple the target qubit with ancilla, and after projections on the like ancilla and target, you effectively can get the collapse of the target state to one of the four, essentially, the projectors. Okay. And the whole, I guess, scheme is that based on the following kind of algebra. Imagine you have a Hamiltonian, they write just the general operator O, right? So it's a linear combination of Pauli products. Okay. So here, just the same thing, but written Pauli products with the sigmas. Now, every sigma, which is Pauli operator, could be written as a linear combination of projectors. Okay. And the idea is that if we have, say, multiple qubits, then within each qubit, we can have 4 projectors. Using these 4 projectors, of course, any Pauli could be described, like any Pauli operator could be described. Why is this the case? Because simply you could see that, okay, so for every projector we have the expression like this. This could be rewritten as well, if you put the psi i's that are written here, what do we get? What are we going to get? For the projectors, we're going to get for every projector, we're going to get 0, 0 with some term, let's say alpha. Then we get 0, 1 with some beta, 1, 0, gamma, and then 1, 1, right, with delta. So we're going to get the sum of this, depending on the I, we're going to get this, right?
So do I need one ancilla per qubit?
That's right.
So I double the register.
That double your register, right? In order to create projectors that are like this, then every projector you could, okay, so every Pauli, let's say we consider a single Pauli case, but then it's just, you could extend it to multi-qubit Pauli, because for every Pauli you do exactly the same. For every qubit you do exactly the same. So let's say you have some sigma q, right? And the idea is to present sigma q as a linear combination of these projectors multiplied by some coefficients. Right? So how do I find these coefficients? That's the only question, because I know the projectors, right? And so if I know these coefficients, then I could reconstruct essentially the form of the operator where I use, instead of Pauli products, I use these projectors, right? Because I know how to measure these projectors using the POVM technique, right? So POVM technique, within each pair of ancilla target will collapse my function, qubit of my function, into one of these 4 projectors, right? And all I want is now to have a coefficient in front of that sort of projector, so that I can learn what the expectation value of the operator is. But operator initially written is a Pauli product, not in my projectors. So therefore, I need to kind of reformulate the Pauli products or Pauli operators in terms of my projectors. And this is this part that is straightforward, because these are vectors essentially in the operator space. These are vectors, and these are vectors in operator space, because as we talk here, the sigma z is, let's say, 0, 0, minus 1, 1. Sigma x is simply 0, 1 plus 1, 0. Sigma y is it's with I, but it's 0, 1 as well, minus I 1, 0. And then we have identity, which is 0, 0 plus 1, 1. Right? So we have this written in terms of the same projections as these guys. Right? And the only difference is that the PIs have the coefficients. So then, of course, these coefficients will be some function of these things. And formally, one can write these coefficients as just simply, well, you could just present. So these guys are not orthonormal, therefore, we cannot just write C's are trace of sigma with P's, but what is done instead, we write every sigma as a linear combination, which we can find from this essentially statement, right? So because we know these coefficients and we know what sigmas are, so it's not that hard to find these coefficients. But it's not just it's easier to, I guess, write the pi in terms of linear combination of sigmas, the I, Q here, right? Let's say this. This we can do with the trace because this is on orthonormal basis. So the D's could be easily found by just doing a trace. So the D's can be found by sigma, the pi's with sigmas, right? And so that allows us to write the pi's in terms of sigmas. And from that, you could, of course, extract how to write sigmas in terms of pi's, right? So it's a linear algebra problem done in the 4-dimensional space, okay? So this is what they do. Eventually, they write their operator in terms now of the product of pi's, but the pi's are for multi-qubit case is just a tensor product of different qubits. So let's say if we have a 2-qubit case, then the pi's become, so the 2-qubit case, the general pi is just a pi for one of these 4 for the first qubit, tensor product with one of the 4, say j for the second qubit, right? And then this procedure could be applied really to individual qubits separately. So we figure out what's the partitioning of pi into terms of sigmas, and then or sigmas in terms of pi, and then and use that in order to essentially extract the how to write our Hamiltonian in terms of the projectors that we can do using POVMs, and what's the coefficient in front. Okay, so that coefficient just comes from the POVM coefficients that are for the individual, I guess, sigmas, and the coefficients of those Pauli products in the Hamiltonian. Okay.
I just don't understand, how is it, so the U in the little red graphic, is that how the pi's are implemented? Or
That's
is that
right.
a general U?
So
Okay.
the U is to implement the pi's.
All right.
Yes. So
Okay.
that is known recipe how if you have one U, you will project to a certain informational complete set of pi's.
Okay, so I double my register, check. I need a U that implements one of the 4 pi's, or no, it implements all of them at the same
It
time.
implements all of
Yes.
them. Then when you do the measurement, it will collapse to one of them.
All right, so I have to measure, I have to bit string, I measure all bit strings.
Right. So these are B's. This is the B's that you obtain.
Yeah.
And
So
they,
it's a computational basis measurement. I
Right.
just need Z.
yes.
Or then.
But one of them, ZZ,
Yeah.
right? So, but one of them will be ancilla, another is, that's why projective measurement in the super system is the measurement that is not projective, but POVM in the target system. Okay. And then you just do the recover how your Hamiltonian will look like in terms of these projectors. What's the coefficient that you need to multiply your results, because you now, as I said, with POVMs you're gonna get this psi p, this multiple p, the multi-dimensional multi-qubit pi, which is a tensor product of corresponding one qubit pi's, and then you need the coefficient in front. So that coefficient that comes from just what the binary results you're getting in the individual 2 qubit sectors. The 2 qubit mean that one ancilla, one target, and the coefficients of that come from the Pauli decomposition of your Hamiltonian.
So that means that compared to like quantum state tomography, I have to just double my register, find magically that U, and then measure just Z strings, roll it, and then I can reconstruct any states compared to having to do 4 to the power of n measurements without grouping.
Well, first of all, where do you get 4 to the n measurements?
If I would measure all Pauli strings, I ignore grouping now.
But okay, so let's say ignoring grouping. So you in the Hamiltonian only have n to the 4 Paulis, so not 4 to the n. So technically, you could measure all of them just using projective measurement.
Okay, no, I meant like with that technique, I can reconstruct the full quantum state tomography. So ignoring doesn't matter if it's a Hamiltonian problem, whatever it is.
Yeah, okay, yes, you can.
So that's what I meant by 4 to the power.
Okay, yes, you can.
With just basically one single, well, several shots of
right, and within each qubit, there are 4 possibilities, right? And of course, that gives you 4 to the n possibilities that you will need to sample.
Yeah.
Right. So, and the question is,
but you sample just in the computational basis. In that.
Sure. But then, in order to get expectation values, these 4 to the n possibilities can have, like you will need to do them multiple times to converge, right?
Yes.
Right, and the assumption here is that will converge fast. Right? Yeah. And you won't need to exponentially many times of doing this 4 to the n, like possibilities of collapses. You won't need to do like too many measurements.
But it means you're forced to explore much larger part of the complete quantum tomography space than you actually need for Hamiltonian, for example. If you do this, you explore the whole quantum state tomography, no? Everything. You can reconstruct every single combination of Pauli measurements that's possible, not just the one that are needed.
Right, but then if you want to find information about all the Paulis, then I believe you will end up with essentially what's going to happen. There are these omegas, right? That you like multiply what you get as a problem. Yeah, you do the collapses in this POVM scheme, and each collapse then you get the statistics, and then there will be also the coefficient on so for that particular type of collapse, you need to multiply or the frequency of that collapse by some omega. And in order to calculate that omega, you use the coefficients of Paulis in the Hamiltonian. And if there will be like exponentially many Paulis in your tomography, you sort of want exponentially many Paulis in order to reconstruct the space. Then yes, there will be exponentially many measurements. So what they benefit is really that these coefficients are polynomial in number of terms, and so they can actually obtain these frequencies well, relatively efficiently. Okay, so this is technically exponentially like tomography is exponentially complicated, but the Hamiltonian result expectation value of the Hamiltonian converges according to their numerics is like within the polynomial. I will show you results next within the polynomial number of shots, right? So millions still, but it's not like something too crazy.
Sorry.
Yeah.
What I don't get is this approach of the pies. The
Yeah.
pies in the 1 qubit case,
Yeah.
the pies allows us to reconstruct any state the
Yes.
1 qubit can be in.
Right.
So if I have a tensor product of, for say, 2 qubits, so
Right.
pi 1 and 2,
Right.
that will be
But with
for all
yeah, sure.
possible
But
states
for the
it can be.
finite number of measurements, you always have approximation to the pi expectation value, right?
So can the pies be tailored to be fitting the Hamiltonian space that I'm looking at the moment? Because if the pies are always exploring everything,
yeah,
I waste a lot of shots for something I actually don't care about.
right. And so in this work, there is some freedom in pies, right? So and they explore that freedom in order to reduce the variance, right? So they do that, but I didn't go too much into the details of that process. But so far, what I've seen in the results and what we have as a comparison to the grouping measurements, and it turns out it's not that great. So first of all, on top, there are these 3 molecules. S is the number of parts, right? And the dashed line is the chemical accuracy, right? So then what they have, different colors, is the SIC-POVM, grad SIC. So there are different schemes of improving the variance. And then there you could see Pauli and the grouped Pauli. But by grouped Pauli, what they mean is like an IBM essentially technique, which is QWC, not the most efficient. And then postdoc who kind of already kind of graduated from my group, but he made this little table where he studied, because this technique that they're using is kind of demanded on the classical resources. So he looked at some molecules, small molecules in different encodings, and compared what the number of measurements would be with the QWC, but with some optimization of the variance. And as you can see, it's, well, maybe here in lithium H, they are, well, kind of winning. But in most other, okay, here also in H2 and BK case, they're winning slightly. And then in other cases, it's not such a great method, especially if this one, QWC-IMA, is trying to reduce the variance within the QWC scheme. This is just a greedy, right? So as you can see, not in all cases, their technique is better. So it's better according to these plots because they compare it with the LF or some very simple non-greedy QWC. So that's my explanation. I spoke with the author, like the last author of this paper, and Sabrina. And so I don't think she knows the details very well, but she was kind of telling me that they were comparing with QWC. And when I asked, okay, what about fully commuting case? What about that? And so like she said that it's in plans to compare, but I never seen anything later.
So if you want to make a startup funding model,
anyway, so this is sort of the story, and the idea is really that if like boil it down to, let's say, if we have a Hamiltonian like this, right? So then if we measure using without any extra qubits, we measure either in Z basis or in X basis. And so that means our sort of projectors will be 4 projectors like this, right, to 1, 1 for projectors. So we will learn only about this part. And then if we do plus plus projectors to minus minus projectors for X part, we'll learn about this part. We don't learn about the whole thing, right? But what their pies are doing, their pies, for each qubit there will be 4. So 4 times 4, 16. So there will be 16 pies. And so with their pies, they are measuring, like they are learning about the entire thing, right?
That's what I tried to say. Yeah.
But again, so what? You learn about the entire thing, and I learn with using this about this and this separately. But I can build the entire thing from the separate measurements by just kind of summing the expectation values, right? And the variance may be better if you learn about the parts rather than you learn about the whole thing, right? So no one guarantees that learning about the whole thing will be better. And it's just nice that you can go qubit after qubit with this technique. And then you don't need to do any grouping. It's kind of universal. It could treat the entire thing.
Well, that's what I meant, like you explore more than you actually need. Because you will explore,
right?
You might explore Pauli's ring.
You have a universal, yes,
not in there.
Right. You have a universal device that will be able to measure any Pauli product. You're right in that sense. And
it could be an advantage if you want to have a Pauli and then data gradient and a hashing or whatever. But it can also be a disadvantage if you're actually just interested in Hamiltonian.
But I also think that it could be an advantage because even like measuring the entire thing, it sounds like a nice feature to have. But if like it's not a classical measure, it's quantum measurement. What this means is that you need to measure again, unless you're in an eigenstate situation.
Yeah.
But you are almost never in eigenstate situation. Therefore, you should always think about how many times do I need to measure. So maybe breaking it down to fragments and having lower variances will be better than having the whole thing.
I agree.
So, and I guess their optimization of the number of measurements is a little bit tricky.
I mean, matching is in the pie in the end, how they actually look like. I can't yet fully imagine how these pie circuits look like.
Yeah. All right. Yeah. So I guess we need to stop here. But the one last point I want to make is that what we somewhat discussed there, you probably get the sense that there's a classical cost associated with this partitioning or optimizations. And then there is a non-unitary quantum cost that is number of measurements, non-unitary because measurement is generally non-unitary. But then the main deal breaker actually near term is the unitary quantum cost, because if you have too many unitaries to do before the measurement, you start generating the sort of garbage, and that is something that is currently hurting all those complicated schemes where the unitaries are more complex than in situations where unitaries are super simple, like qubit-wise commuting, for example, right? So yeah, and we will talk a little bit about error mitigation and next time, I guess, right? Okay. That's it for today. You could stop.